All right. Well, welcome back, folks. We left off yesterday with this discussion of electron configurations and writing them for molecules, and that is for compounds. And so we need to be able to do this, but what we need to remember then is when we write out these electron configurations for these molecules, the process by which we write out these electron configurations for the molecules is very similar to the process that we use to write out the electron configurations for atoms. And so I left off well with this particular slider to remind you, and for those of you who've had me before, you've seen this. Remind you then that when we did atomic the electron configurations for atoms, we had listed then we basically developed an energy diagram for the orbitals, the atomic orbitals, and how they compare with one another, and then we use that to start filling in the electrons and obtain the electron configuration that way. Okay? And so what we did here, and what you'll notice here then, and I'll pick up with this then, is that we have our energy diagram. So it's energy here, and the atomic orbitals listed in order of ascending energy. Okay, with the 1s orbital lowest in energy, and we proceed forward up the energy scale with the rest of the atomic orbitals. And so what we have obtained here is an energy diagram of atomic orbitals. And so what did we do to get the electron configuration for an atom, for example, carbon here? Well, first of all, we had to figure out then how many total atoms comprise this particular atom here. I'm sorry, how many total electrons comprise this particular atom here. And we saw then that with the atomic number 6, that represented then that we have to locate 6 electrons. There are 6 total electrons that we have to identify, we have to find the location for. And so we went ahead and proceeded by using this energy diagram, and we started to fill in the energy diagram with these electrons. And so this particular atom is made up of 6 total electrons, and we have to locate those 6 electrons. And that's what an electron configuration is, the location, locating the electrons that make up a particular atom. I want you to keep that in mind, because that's exactly what we will do with the molecule as well. Yeah? All right, so with that said, then we always start at the lowest energy level first, and that's the Aufbau principle tells us that we start filling that in. And the maximum number of electrons that can fill in a particular orbital or energy level is going to be 2. That's the Pauli exclusion principle. We will be using these exact same rules to fill in the molecular diagram as well. Okay, so for doing the molecule, we'll be doing the same thing, okay, but we'll be using molecular orbitals instead of atomic orbitals in this case. Okay? All right, so that's 2 out of the 6, and so we have 4 more. So according to the Aufbau principle, we go up to the next energy level, and we fill that in with 2. Okay, and so with that said, then we have a total then of 4. We still have to count for 6, and so when this 2s orbital is filled, we go to the next energy level, the next energy orbitals, and that's going to be the 2p, and then we start filling that in there as well. But we only have 2 more to account for, and so therefore the 2 remaining electrons will spread out across this energy level, okay, because of Hund's rule. And Hund's rule tells us that atoms, electrons then, when they will spread out because they repel one another. All of those rules that we use, the process by which we use to obtain the electron configuration for an atom, we use also to obtain the electron configuration for a molecule. Okay. All right, so with that said then, to finish out, then we just list down what we have here. So we have 2 electrons in the 1s orbital, so we write down 1s, and we have 2 electrons in the 1s orbital. Then we go to the next one, we list that as the 2s, and we have 2 electrons in the 2s orbital here, and then finally we have 2 electrons in the 2p orbital, and there it is. And there is the electron configuration for the carbon atom. So this is the atomic electron configuration. Okay. So with that said, then, if you remember that configuration, if you remember that and the process by which we use to write out the electron configuration for an atom, we're going to do the same thing, and we're going to use this same process that I just highlighted here for you, okay, to write out the electron configuration for a molecule. Okay, and so now what we have here, folks, is instead of having a single atom of carbon, we have then what we're going to look at is diatomic carbon. And so we're applying then the concepts that we learned for the atom to understanding how molecules form, the interactions that forms these molecules. And so what we've been doing is we've been looking at very simple molecules, these diatomic molecules that are homonuclear in nature. Homonuclear meaning then that it's the same atom bonded together. And so here we are, we're looking at diatomic carbon. On the previous slide, we were looking at a single atom of carbon. We found the electron configuration for that. We want to be able to write down the electron configuration for diatomic carbon. Okay, so that is, what's the interaction, if it exists, if the hypothetical dicarbon exists, what would the interaction be for that? Okay, so we're going to write out the electron configuration for this. And so just like what we did with the carbon atom, the single carbon atom, we're going to do the same thing with diatomic carbon. The first thing then is identifying then the number of electrons that we have to locate. Okay, so with a single atom of carbon, we had to look for 6 electrons, 6 total electrons located. But remember, with the molecule, when we are identifying the electrons that make up this molecule, we are looking only at the valence electrons. Okay, we are only looking at the valence electrons. And so with that said, then make sure you keep that in mind, because with the valence electrons, and let's go ahead and write out the electron configuration for carbon here. Okay, so carbon again is the carbon atom is 1s2, 2s2, 2p2. That's what we obtained in the previous slide. Okay, so with that said, then when we look at the diatomic carbon, okay, we are only looking at these electrons here. These electrons from each carbon. Okay, so let's take a look at this here. So let's imagine this is carbon number 1 here. So we'll call this carbon number 1 on this side, and then carbon number 2 on this side. I'm sorry. Let's call this carbon A. So this is carbon A, and this is a different carbon B, and so that you don't confuse this with dicarbon that we're looking at here. Okay, so let's go ahead and do this. So we have 2 atoms of carbon, carbon A on this side, carbon B on this side. Okay, now what we're going to do then is we're going to analyze 2 electron. Okay, and so hopefully you recognize this is the energy diagram. Okay, this is the molecular orbitals. Okay, these are the molecular orbitals that form when 2 atoms get together, and very much like what we saw on the previous slide with the atomic orbitals, what we've done here is we've listed the molecular orbitals in order of ascending energy. Okay, with the sigma 2s bonding, sigma 2s antibonding here, sigma pi, sigma 2p, pi 2p bonding, antibonding, and then pi sigma 2p antibonding here. And so we've listed all of the molecular orbitals in ascending order, okay, of energy here. Now, with that said, then there are two possible orderings for these molecular orbitals. And we saw then how that happened with the diboron. And so we saw then that in certain diatomic molecules, in certain molecules then, the energy for the pi 2p and the sigma 2p, the pi p and the sigma p, they flip order. And so there's where we get the second possibility here. So unlike the atomic orbitals, where we really only have one way that we can order the atomic orbitals, with the molecular orbitals here, there are 2 possible ways that we can arrange the molecular orbitals themselves. But again, what we're going to do is we're just going to go and we're going to fill in these molecular orbitals here. Okay. All right. So with that said, then let's go ahead and fill in what we have here. So what we have here, these. So again, we're only focusing on this here. So since we have 2 carbon atoms, we're going to account for then 8 total electrons. We have to account for 8 total electrons in the molecular orbitals here. Okay, so we have to account for the position of 8 total electrons, because it's these 8 electrons here that holds the carbon atoms together and makes this molecule. Without these 8 electrons here, and again, we don't worry about these core electrons here, they do not participate in bonding, so we don't have to worry about locating them on this energy diagram. The energy diagram here is only for molecular orbitals, and these molecular orbitals only contain valence electrons. So we are only going to examine the valence electrons for any atom. Okay? For any molecule. All right. So with that said, then to start out, let's go ahead and label this here. So these dashed lines here represents the atomic orbitals right now. So we have 2 s orbitals from carbon A, 2 s orbital from carbon B. These atomic orbitals here are a little bit higher in energy. So this is the 2 p orbitals from carbon A. This is 2 p orbitals from carbon B. Okay. All right, so what we have here on this energy diagrams, we've listed them atomic orbitals and the molecular orbitals here. So atomic orbitals are on the side. Okay, these are the atomic orbitals. These dashed lines represent the atomic orbitals. Okay, and the one in the middle here, those in the middle represents the molecular orbitals. Okay, all right. So before we proceed, I need to give you some information about dicarbon here. Okay, so you need to have some information about dicarbon in order to figure out then which electron configuration will be the correct configuration. Right, so let's go ahead and do this here. We know then that dicarbon, if we put it inside the magnetic field, okay, that the dicarbon then is diamagnetic. Okay, diamagnetic meaning then that it will, it has it will have paired electrons, and as such, then it will not be attracted to a magnetic field. Okay, so paramagnetic molecules have only a single electron; they get pulled into a magnetic field. Whereas with diamagnetic compounds, all their electrons are paired, and we only have paired electrons. So that's what we do with this piece of information here. If we know that this this particular molecule is diamagnetic, we know that all 8 electrons are paired. Okay, that's going to be important in figuring out which one of these electron models will allow us to is the one that we use for dicarbon. Okay, but you want to keep that in mind. All right. So with that said, then the last piece of information that we're going to use then to figure this out then is that we have you will use photoelectron spectroscopy, and that's what we're gonna. My hope is that we'll start that with today. Okay, with photoelectron spectroscopy, then we see then that you have 4 electrons then that are highest in energy. You have 4 electrons that will have higher energy than all the other ones. Okay, so you have 4 that are higher in energy than every other electron. And so based on that, we're going to go ahead and we're going to figure out which one of these 2 is correct. Okay, let's start filling out this table then. Okay. All right, so with each carbon then, it has 2 electrons in the s orbital, in the 2s orbital. Okay, so we have 1, 2 here, and then for carbon B, I'm sorry, this should be carbon B, we have 1, 2 electrons here. Okay, all right, for each carbon then, you have 2 electrons in the 2p orbitals. So let's go ahead and write that there. So what we've done here is all we've done is we've located the valence electrons for the individual carbon atoms. So when they get together, let's go ahead and do this. Each atom will contribute an electron. Okay, so that means then this electron will contribute 1. This atom here, this carbon will contribute 1 electron to the molecular orbital, and this one will contribute 1 also. So that can take care of 2 out of the 4. The remaining 2 then will, according to the Aufbau principle, fill in the next energy level. Okay, and so there we've accounted for the 4 electrons here from each carbon. So these 4 electrons will occupy a sigma bonding and a sigma anti-bonding molecular orbital. Okay, and so we're just filling it in. What comes next? Well, we got to fill in this next. Okay, so the sigma 2p molecular orbital has to be filled in next. And so it can hold a maximum of 2. So 2 electrons from each side will fill in right there. Okay, so you have that right there. And so the remaining 2 electrons then will fill in the pi p orbitals here. And since you have 2 at this particular energy level, they will spread out according to the according to Hund's rule. All right. So for this option here, then, the electron configuration. So using this, then we're going to write out then the electron configuration here. So that's going to be then sigma, okay, 2s, okay, and there's 2 electrons there. So that's the first one here. The next one then is going to be sigma 2s star, the antibonding, and there's 2 electrons here. Okay. Then you have what's filled in next, sigma 2p, and you have 2 of those. And then finally, then we have then the pi 2p, and we have 2 there. Okay, all right. So the first electron configuration, the possibility here is this one. But unlike the atomic orbitals, there is a second possibility on this side here. And so let's go ahead then. So this is option number 1. Okay, option number 1. Let's go ahead and do the same thing, and we'll fill it in the same way here. Okay, so this is going to be carbon A. This is going to be carbon B. So let's fill it in here. This is going to be the 2s orbital for A, 2s orbital for B. This is going to be the 2p orbital for A and the 2p orbital for B. Okay, All right, let's start filling in the valence electrons here. We have 2 here for each one of these atoms. Okay? And you have 2 electrons here. And so these are the atomic atomic electrons from the atom here. All right, so they come together. And so they're going to fill in the lowest energy molecular orbital first. Then they're going to continue to fill up. Okay, now you have here, for this particular model of the molecular orbitals, you have now the 2 pi molecular orbitals, lowered energy, and so these 4 here are going to fill in here. So you have then 1, 2, okay, and then remember they will have to fill in this energy level before they jump here. So that means you have then 3, 4. Okay, all right. So the electron configuration that we obtained from this model here is going to be then sigma 2s, and we have 2 of those. Okay, we have sigma 2s antibonding. We have 2 electrons there, and then we have then pi 2p, and we have 4 electrons there. Okay, all right, so the question then is, of these 2 electron configurations, this one or this one, which is the correct electron configuration for dicarbon? Okay, so understand this. In both electron configurations, we've accounted for 8. Go ahead and count it here, just like what we did with the atomic orbitals last year. You just count up the number, add up the superscripts here. You have 2, 4, 6, 8. So this accounts for 8. Here we have 4, 6, 8. This accounts for 8 as well. So both of these so far have 8. Okay. Now let's check then the first piece of information that we need. We're going to use to determine which one of these is correct, and that is that the dicarbon is diamagnetic. What's that mean then? That each carbon, dicarbon has no unpaired electrons. Okay, has no unpaired electrons. Well, if we take a look at this right here, okay, if we take a look at this right here, we have 2 unpaired electrons right here. Okay, so let's go ahead and let's take a look at this here. The fact then that this model here, this molecular orbital diagram here, shows us that we have 2 unpaired electrons here. If that were the case, that would indicate then that the carbon atom would be paramagnetic, which means that it would be pulled into the magnetic field, and we know that it does not. Okay, no, that it does not. And so therefore then, this must be the correct electron configuration right here. That alone right there, the fact then that the dicarbon C2 is diamagnetic, okay, allows us to confirm then that this is the correct electron configuration for C2 dicarbon. Okay, so that's what we use this information for. We use that to confirm then what we already to decide then which one of these 2 electron configuration represents the correct electron configuration for dicarbon. Okay. Now, with that said, that we can use also photoelectron spectroscopy to get that done as well. And we said then with photoelectron spectroscopy, we have 4 electrons that are highest in energy. Okay, and so there are the 4 that are higher in energy than these 2 here. Here, we only have 2 electrons that are highest in energy instead of 4. So these 2 electrons are higher in energy than these 6, and that doesn't quite fit with the spectroscopic data as well. Okay, so with that said then, that is how we know that the electron configuration then for dicarbon is this one right here. So we write out the electron configurations for each one of these molecules, and then we will confirm it with the data that's given to us. And so on the AP exam or on what you'll see for me, we would have to give you this information here. We'd have to tell you that the magnetic properties of the molecule, and then we'd have to give you the spectroscopic data here for you to confirm which one of these would be correct. Okay? All right, so with that said, what I would like you to do, and I would like you to fill out this next table here. Okay, so let's go ahead and save this. Okay, and what I'd like you to do, let's see this again. I want you, and you go ahead and print out this here, okay, or fill it out, okay, and then print it out and fill it out, and then take a picture of it and then submit it. We're running low on time here, so what I would like you to do is I want you to write out the electron configuration for dinitrogen. For dinitrogen, Okay, and so let me give you the data here that you'll need in order to get this done. Okay, so what do we know about dinitrogen? First of all, dinitrogen then is going to be diamagnetic as well. So we know that diamagnetic, we know that about N2. Furthermore, we know then with diamagnetic from photoelectron spectroscopy, okay, that we have two electrons that are highest in energy, that are higher in energy, than all other electrons. Okay, so we have two all by themselves that are higher in energy than all other electrons. So use this evidence here, use this experimental evidence here to decide then which one of these, to decide then the electron configuration, what is the correct electron configuration for dinitrogen. So practice this, folks. So what I would like you to do is just quickly print out this particular slide here, do dinitrogen, exactly what we did in the previous slide, work it out that way, and then submit this to me today so that then we can use this to go over, finish going over this tomorrow. So I will continue to post. So just like what we've done the last 2 weeks, I will continue to do lectures for you on Saturday over the weekend. Okay, and so post this, okay, and then have this with you tomorrow so that we can go over it together. Okay. All right, so good luck with this, folks. And then if you have any questions, if you want to go over this, then come by and see me after school today, 1:30 to 2:30. I'll go over this with you, okay? And then we'll practice another one. So practice this here, folks. I know it looks crazy, it looks really difficult, but the more you practice this, just like with the atomic orbitals, I'm pretty sure at that time that looked pretty difficult as well. And so we're stepping it up here a little bit, folks. We're stepping it up here now. We're using the same process. But this time, though, we're trying to write out the electron configuration for a molecule rather than for a simple atom, okay? All right, folks, so yeah, good luck with this. Try it, and then do your best with it, and then we'll go over this one tomorrow, okay? All right, folks, have a good day.